In this module, we're going to take a closer look at fuels and specifically in fuel properties. So we've already looked at the equations, at some of the combustion and what goes on behind the scenes or chemically in the engine. Now we're going to look at some of the more physical fuel properties and how they're critical to engine operation. We'll see how they factor into efficiencies and so forth as well, and converting the energy. So specifically what we're going to look at is energy content. So that is going to be measured in how much energy is in it. So either in English units it's in a BTU, British thermal unit, or in kilojoules in the metric system. We'll look at energy density, so a little bit, and it's not as critical, but how much energy is in a unit of the fuel, either on an energy per volume basis or it could be on a per weight basis as well, related with the density. So the energy density, physical density, again, these are not as critical, but for moving fuels in and out of an engine, they can be kind of critical. What we will spend some time on are the ignition properties. So we'll talk about octane and cetane and what we see at a fuel pump, why that's critical and what those numbers mean, and a little bit about flowability. So let's dive into this and start looking at the energy content of fuels. And so we want to look at the first of all, we'll start with the spark ignition engine. Fuels we typically use in a spark ignition engine. You can see there's typically either gasoline or ethanol. Those are the two fuels that we use, or some blend between the two. And we're going to see right off that we look at the energy content, the energy density there. You see gasoline comes in at about 115,000. And this is in English units, so those are in BTUs per gallon. We can convert them easily to metric system. But relatively, the ethanol is only at 76,000. So you can see it has much less energy in it, okay? So, and that's kind of odd when you think about any of you that are racing fans, and you realize that that a lot of performance racing fuels is an ethanol-based fuel, and you think, well, wait a minute, there's not as much energy in that fuel. Well, no, there's not. But the difference is on the last line down there, the octane rating is different. So the octane of gasoline, anywhere from 87 to 95, you see those numbers on the pump, and we'll come back and show what those numbers mean and what they are. But the ethanol is a much higher octane rating, and so that's going to be the difference. So it's not energy density, it's not how much energy is in the fuel, there's actually less energy in ethanol-based fuels. There's the octane rating is going to be different. We'll see how that makes a difference. All right, so typically most of our gasoline supply is a blend of ethanol, and ethanol is as an oxygenator, and I mentioned that in the last module where that we add oxygen molecules or oxygen molecules into the fuel molecule. It makes it burn better because we don't have to be as concerned about the mixing, how the fuel gets mixed, or how the air gets mixed with the fuel in the combustion chamber. So there's already some oxygen right there in the molecule, so that helps us out quite a bit. And it's a replacement for MTBE, which is methyl tetrabutylethylene. It's a compound that used to be used in gasoline. It's a petroleum-based compound that was an oxygenator, did the same thing as what ethanol did, to add some oxygen to the fuel. So there's not as much of that anymore. Almost all of our fuel is an ethylene, is an ethanol blend, about 10% typically. And most of our vehicles now are flex fuel vehicles, and you see that flex fuel symbol or something similar to that on a lot of vehicles. And that tells me that, hey, that vehicle, it could burn ethanol if it wanted to, up to 85%. And so we do have some ethanol E85 supplies. It's not widely available, but in the United States, we do have E85 available at some pumps. Now you go to other countries, and this becomes more critical. I traveled quite a bit to Brazil a number of years ago, and their fuel supply down there, their gas stations are a whole lot more complicated than ours. They have 4, 5, 6 different fuels that are available. We basically have 2 or 3, a couple different octanes that are available in the gasolines. Well, they have the couple different octanes. They have have some with the pure alcohol or almost pure alcohol, the E85, different blends. And so it's a very complicated thing. They all have different prices. And so they need to understand, okay, how is my car going to perform on these different fuels, and what kind of fuel do I put in my vehicle? What would be the most economical for me? So it's a lot more complicated for them. So we don't have to deal with that because we don't have that supply readily available to us. Okay, but that's the difference, and we start to see that now with the different fuels that are commonly available. If we go to the compression ignition engines, we see the same kind of thing. So biodiesel is kind of the fuel that, again, 5-6 years ago, there was a lot of interest in that, or even a little bit more. Everybody was trying to make biodiesel out of French fry oil and everything else. And in the lab, we'll actually put some French fry oil in an engine and burn it. So you can actually, in a diesel engine, you can put cooking oil straight into it, and it will burn cooking oil. So we'll see that. Exhaust smells like French fries. It's kind of funny. But anyway, there's some different amounts of fuel in there. So the key, again, like with the ethanol, the biodiesel has a lower energy content than we have in diesel fuel. So 129,000 BTUs per gallon versus 118. But again, the big difference is the cetane rating. So the cetane is quite a bit higher, and a cetane is like the octane for diesel fuel, and we'll define what that is here in just a minute. So that gives us some advantages there. So typically, a lot of our diesel fuel supply now is a blend. So we talk about B5, that means 5% biodiesel in the blend, and you'll see blends up to 20% all over the place. So there's a difference there. Now, one of the challenges with biodiesel, we look at some of the other properties there, the cloud point, and I'll talk just a bit about cloud point because these fuels, when they get cold, they will turn into a gel. And so the common vernacular, people will, in wintertime and winter climates, will have trouble with their diesel engine. They say, my fuel gelled up. Well, what it did is it reached a cloud point where it started to turn into a solid. So it froze, basically, is what that means. And so the biodiesel has a much higher cloud point, which means it doesn't have to get as cold before it starts to turn into a gel. And so you have some issues there that you need to be thinking about when we're managing biodiesel supply. So even though we can get it into the engine in a warm summer day, we might have problems on a cold day. And so there's lots of stories that people can tell about, running machinery in the summertime, and they have biodiesel supplies in the summertime. In the wintertime, they go to move the thing in the barn, and all the fuel is gelled up because it was a summertime fuel, and it wasn't blended and didn't have the right additives and everything to keep it flowing in the wintertime. So cloud point is a critical thing for us, and the flowability of these fuels to be able to keep them working. Okay, so again, we see some differences. So these are all fuels, and most of our engines can burn both of these in different proportions, biodiesel, ethanol, and everything else. So that is going to affect our performance. So what effects does it have on our performance? Well, two ways that this could manifest itself. So it can either manifest itself as a power loss or as increased fuel usage. So if I'm a farmer with a tractor out in the field, or a truck driver with putting diesel fuel over the road truck or something like that, what's going to happen if I go from a petroleum-based diesel to a biodiesel? So what am I going to notice? And this table there kind of shows you a little bit, hey, if I just got a 2%, I'm not going to notice anything. If a 20%, I'm going to notice about a 2% drop. Okay, will I notice that? I might notice a little bit less power going up a hill, or I may notice some fuel mileage difference or something like that. 100% biodiesel, I'm going to notice a 10% difference. That's going to be significant enough for me to notice what's going on. Again, this could manifest itself in two different ways when I change fuels. That biofuel has a lower energy density, so it doesn't have as much energy in it. So how will the engine respond to that? Will it actually use more fuel to do the same amount of work, or will it put the same amount of fuel through and just not be able to do as much work and not be able to have as much power? And you'll see that happen, maybe combinations of those different engines depending on how they're controlled. If it's a very simple mechanical control engine, if it's some of the more modern engines with all the electronic controls and everything, they may respond a little bit differently, or different things might happen with them. And so those are things that we can look at. We're actually going to try to look at this in a later lab this semester. So we have a way that we can measure the fuel content going into an engine. So we have a small diesel engine down there, and we can abuse it and pour all kind of weird stuff into it. And so we'll do that. So we'll have some diesel there, we'll run the engine, get a performance curve, and then we'll change it out and put some different fuel in. So we can put some cooking oil into it and see what happens. We can put whatever into it. And then we'll say, okay, what happened? Did it burn more fuel or less fuel? Did it get more power out of it, the same amount of power, less power? How did the engine respond? So we'll try to determine that, okay? So those are the things that we're going to look at. So that's the kind of performance that we'll see with the different fuels going into the engine, as long as the engine can burn it. And different engines, again, will compensate in different ways. So some of the modern engines, they have a lot of sensors in the fuel and in the airstream that they know how much oxygen is in the airstream, how much oxygen is in the fuel is the nature of it. And so they can actually change a lot of the operating parameters of that engine. So they can change the timing of the injection or the spark. They can change how the valves open and close and so forth, and all that will change how that engine can utilize the different fuels. And so some of the modern engines really compensate very nicely for them. So the engine we're going to use in lab is an older engine, just a mechanical control, very simple fuel injector. And so we should be able to see some differences there and start to understand what's happening with that particular engine. So that's the performance difference you would see. That's compression ignition. Now what about my truck that I put on the road? And I looked up the venerable Ford F-150 just to see what would happen with different types of fuels in it. And you can go to this website, fueleconomy.gov, and for any vehicle, it'll tell you what the real fuel mileage is, which should match pretty close to what's on the sticker. But the nice thing is you can actually look at different fuels in there. So they'll have some lines, some ability to look at how that vehicle would perform on ethanol, for instance. And so this particular truck, I looked this one up, a 2017 Ford F-150 on E85. There you can see that it has about a 13 or 18 city and highway, whereas on the gasoline it'll go 18 and 24. So you can see the difference in the fuel economy that you would achieve with ethanol fuels versus the petroleum-based gasoline fuels. So again, we don't have a lot of E85 available, so it's not a big decision for us, but a lot of other countries do. They have to think about, okay, what is my economy with ethanol? Ethanol is going to be cheaper. Is it enough cheaper that I would make fiscal sense for me to do that? And so we have to go through those decisions. So that's fuel economy, what goes on there. Now, I kept dancing around this octane and cetane thing. Let me come back to that and understand that. Octane and cetane. Octane and cetane are a way that we quantify those auto-ignition properties of the fuel. So let me back up a little bit. So the auto-ignition properties, remember we talked about that in an earlier module. If I take an air-fuel mixture and I compress it enough, it's going to ignite. It's going to start to burn. It'll combust, okay, just based on the pressure. So the octane to cetane tells me how much pressure does it take to make that fuel combust, okay? So look at octane first, because that's a gasoline. We see that at the pump. You see that yellow sticker on the pump, and you decide whether you put 87, 89, 93, or whatever in your vehicle. You got that fancy vehicle, and it was 93 octane, and do I really have to buy this expensive fuel for this vehicle? All right, so the octane measures the pressure, indicates the pressure. The higher the octane, the higher the auto-ignition pressure. Okay, so if I have a higher octane fuel, I can compress it more to a higher pressure before it's going to combust. Lower octane fuels, they won't combust as quickly, or they'll combust quickly at a lower pressure. Okay, so if I have an engine, let's think about this a little bit. If I have an engine that will, and I'll come back to that. We'll talk about the implications of that in a minute, of what those implications are. But that's what octane is, okay? It measures that. Cetane is the same thing except the opposite. So octane, we want to make sure that pressure is high enough that it doesn't auto-ignite before I light it with the spark. and so I need to have a higher number, means a higher ignition pressure. Cetane goes the opposite way. In a diesel engine, I want that stuff to auto ignite, so I want it to be able to, and you know, especially with a cold engine, when I'm starting it up, I don't have a lot of pressure in that engine, the temperature's not there of the engine, so they're harder to start. So I'd really like that fuel to have a lower auto ignition pressure. So in a cetane rating, which is similar in a diesel fuel, the higher cetane means a lower auto ignition pressure. And there's actually a conversion where you can convert between octane and cetane. We could actually use the same numbers, but people like to have a higher number meaning something better. So a higher number means lower auto ignition pressure. That's better in diesel fuel, okay? So cetane, octane, kind of the same things. Cetane goes the opposite way. So higher cetane number means a lower auto ignition pressure. Higher octane means a higher auto ignition pressure when that thing will light off. All right, so let's talk about the implications of this. Let's talk about cetane first. Again, diesel engines, compression ignition engines, that's where it's important. So the higher cetane number means a lower auto ignition pressure. So it means, again, I mentioned that when we're starting an engine, when it's cold and the engine is, you know, you're turning it over with an electric starter and it's not spinning very fast, we don't build up a lot of pressure. And so the pressures in that piston are pretty low. And if I inject fuel in there and the pressure is not high enough, the fuel is not going to burn. So it's just going to stay in there until I push it out through the exhaust. All right, so I want that fuel to have a low auto ignition pressure, and so that's where the cetane will help me out. And if I have a higher cetane number, that means when I start it up, it's going to start easier. So cold starting is going to be a lot easier because it'll burn easier. A lot of these diesel engines at really low RPMs and they're running slow, if you're around trucks and stuff like that, they rattle and bang and hammer and make a lot of noise. So if I have a fuel with a higher cetane number, it's not going to make as much noise. So it's going to be a little smoother running engine. It's going to sound a little bit nicer. So that's one of the nice things that biodiesel does to us. Makes the engine sound smoother, okay? Makes them run a little bit nicer. All right, but here's the weird thing about that. So we think, hey, I'm going to spend extra money for high cetane fuel so that it burns better, but I might get higher emissions, really? So what can happen? And again, that critical thing, when I inject that fuel into that cylinder, in that space on the top of the cylinder, I want to be able to get that air and the fuel mixed together. So if I inject that fuel, it comes out of the injector, and it's a real low auto ignition pressure, it's going to start to burn right away. And what's going to happen is it may burn before it gets distributed all the way through the cylinder and gets mixed with all of the oxygen molecules that are in there. So I might get this burning front that kind of goes out through the piston, blocks some of the fuel that's coming in behind it. I get incomplete combustion, and so I may end up with actually more emissions coming out of the engine. And so, you know, when we think about biofuels and all that, a biofuel doesn't automatically mean less emissions in the engine. If the engine is not designed, the injectors are not timed correctly to make all that happen. And the engine manufacturers will do a lot of unusual things to make them burn better. For instance, they might do a pre-injection on some of these engines where they actually put a little bit of fuel in there and it burns, and then they put the real shot of fuel into it later, and what that does is it creates some turbulence and creates some different mixing so we get more complete burning and stuff like that. So there's a lot of things that manufacturers will do, engine manufacturers and designers, to be able to increase that. Okay, but that's the implications of what cetane will do for me. Octane rating. So does that mean a cleaner burn? Yeah, it could mean a cleaner burn if the engine is designed to do that, okay? So less knock. So again, think about that. So if I've got an engine that is designed, it's got a higher compression ratio, so it's designed for higher octane fuels. So I can put a little bit more compression ratio in that. You go back to that PV diagram, that shoves that PV diagram back to the left a little bit more. And so, you know, it opens that up and gives me more pressure, gives me more power out of it. So, hey, I can go with a higher compression ratio, use that high octane fuel in there. It's not going to auto ignite until I put the spark to it. But if I put a low octane fuel in there, and that piston's coming up, it might hit that auto ignition pressure before I give it the spark, and it's going to burn at the wrong time. And if it burns burns while the piston's still coming up. That's where you'll get a force pushing back down on the piston, and when the crankshaft comes up over the top, it does some weird things, and so that's where you get some knock and hammer and everything like that. You can actually, we had some old tractors when I grew up on a farm. They were 50s manufactured gasoline engine tractors. And on a real hot day, the engine would build up enough heat, and we never bought real high octane fuel. We bought low octane fuels. And sometimes when you turn them off, when you turn off a gasoline engine, you just turn off the spark, and that should not ignite the fuel. But the engine is sometimes hot enough that the fuel will still ignite. And so you shut the engine off and you sit there, and the engine still runs for a little bit. It sounds terrible. It rattles and bangs and hammers and jumps and makes some funny noises, but it'll run a little bit. And so we'll call that in the vernacular to say that engine is dieseling. So that gasoline engine is dieseling, which means it's running on the auto ignition properties of the fuel. It keeps on going even though I turned the spark off to it. So higher octane fuel wouldn't do that. It wouldn't diesel because it's not going to reach that auto ignition pressure. So go back to the auto manufacturer that tells you, hey, this car needs to have 93 octane fuel in it. You got to go buy that really expensive fuel and put it in your car. Do you really have to put that really expensive fuel in your car? I wonder if it's a conspiracy between that auto manufacturer and the fuel companies that like to sell that expensive fuel. Yes and no. There's some difference. So here's the bottom line. If your engine will run on low octane fuel, run it on low octane fuel. You're probably not going to get any advantage from a high octane fuel in that engine. All right, if it runs well on a low octane fuel. And that's the key, okay? If it's got a low enough compression ratio, it's not dieseling, it's not hammering, it's not knocking, and stuff like that, use a low octane fuel. Again, you're not getting any more energy content out of the high octane fuels. If your engine doesn't run well on it, maybe the manufacturer has a higher compression ratio. And again, on the modern engines, the manufacturers are doing a lot of different things. So they're actually doing changing the timing on the spark and stuff like that. They can do that dynamically, as the engine operates. And so they will actually compensate for higher octane fuel. So some of the engines actually do perform a little bit better for higher octane fuels because they're taking advantage of that high that high octane property on the high auto ignition pressure. So they can do some earlier sparks and things like that. So that's kind of the story on that. So what I tell people is, hey, put the low octane fuel in it. If it sounds good and gets good mileage, leave it run. All right. If you need to, if it doesn't sound good, then you got to run the higher octane stuff in it. All right. Let me go back to racing fuels a little bit, and I talked about that a minute ago. I said, hey, these NASCAR and all these folks use ethanol with the low energy content. Yeah, it's the real high octane. So a lot of that racing fuel is well over a 110 octane. So you saw pure ethanol's 117 is what its octane rating is. So that means they can run really, really high compression ratios. And they'll either do that. They'll either run a real high compression ratio in the engine, or you'll see a lot of performance cars like drag racers and stuff like that. And the engine is very indicative. They'll have a blower on it. So it's basically like a turbocharger, but it's mechanically operated. And you'll see a big wide belt on the front of the engine that goes down that runs on the front of the engine. So sitting on top of the engine is this blower. And that blower is shoving air into the engine. So it's not running off the exhaust. It's actually running mechanically off of the crankshaft. And so they'll keep the engine inherently will have a pretty low compression ratio, but they're shoving a lot of fuel and air into that engine with that blower. And so when that piston comes down, they shove it in, put a lot of it in there, and then when that piston comes up, we got some really high pressures in there because we put so much material into that cylinder. And so that's how they can get a lot of horsepower out of them. Even with a relatively low, some of those performance engines are no more than about 6 to 8 compression ratio, so fairly low compression ratio. But with the blower, they put a whole lot of that material in there, get the high pressure, and then light it with a spark, and so it lights when they want it to. So that's how we take advantage of that high octane rating. Higher pressures get more performance out of those engines. Okay, we're building up a lot of heat, so you'll see those blowers on short performance type things. So drag racers where they run a quarter mile and shut them off and that's it. Tractor pulls and stuff like that, same thing, they're not running. So NASCAR, where it's got to be more of an endurance, you won't see those blowers kind of things, so they're going to run just a higher, the higher compression ratio in the engine to be able to keep track of that. All right, so they got to watch temperatures, got to watch pressures, and so forth to keep all that going. So that's octane and cetane, what they mean to the engine, how they change the performance, and so forth. All right, so do I have to modify my engine to run all this? And I've kind of hit it all the way through this, that most of our modern engines have a lot of pretty sophisticated electronic controls in them, so they can do a lot of things. They can change the timing of the injections or the spark. They can actually change the opening of the exhaust and the intake valves, when they open, how much they open, how long they stay open, so forth. So they can change all that dynamically. So they're doing a lot of things within the engine to compensate for different amounts of fuels, different atmospheres. By the way, something I didn't mention on the octane, if you ever travel to the Midwest, and the first time I went to Colorado, I love to go to Colorado, enjoy the mountains up there, but you get up at high elevations and you go to buy fuel at a gas station. Around here we have, at less than 1,000-foot elevation, we have 87, 89, 93 octane. You go to the Midwest at high elevations, their low octane is 85, so they go 85, 87, 91, or 89, something like that. So their low octane is 85, and I saw that and I was like, oh man, I got to spend more money for the fuel to get the 87 that I run down there. Well, no, your engine will run at a lower octane at a higher altitude. And why? Well, think about the air that you're putting into that engine. It's a thinner atmosphere. There's not as much oxygen in that air, so there's not as much air to go in that engine. So your pressures are going to be lower. So with the same compression ratio, you're starting at a lower pressure, and with that ratio, you're not going to get up to higher pressure, so you're not going to have those auto ignition properties with the dieseling and the knocking and stuff like that. So you can get away with a lower octane fuel at higher elevations. So you'll see that. So that's one of the things that you'll see going on up there. So again, the manufacturers can do a lot of that kind of stuff. Some of the things you have to watch though, and I mentioned this for biodiesel because this has gotten us into a lot of trouble in agriculture over the last couple of years when we go to biodiesel. Biodiesel loves rubber, and I mean loves it for lunch, so it will actually dissolve rubber components. So if you have real rubber components, natural rubber, biodiesel will eat it apart. So it'll just dissolve it and get rid of it. So gaskets and hoses and stuff like that will tear them apart, so you got to watch that. But again, manufacturers will adjust the timing and things like that on the fuel. So can I put biodiesel in my engine? Yep. So watch carefully the hoses and all that kind of stuff, and you may have to replace them with some synthetic. And most of the engines now are manufactured with a Viton or some other synthetic rubber materials that aren't affected by biodiesel, so they can handle the higher concentrations of biodiesel. But if you get above 20%, then you've got to really think about it. Anything less than 20, you can pretty much put it in and go with. Okay, same thing with the ethanol fuel. So any automobile that's manufactured after 2001 can handle up to 20% ethanol. So that's a federal mandate. So if you've got a model year newer than 2001, you can put up to 20% ethanol in it. Other biodiesel, it's toxic, it's non-toxic and biodegradable, so it falls in the ground, it'll eventually degrade, so that's a nice thing for the environment. It's a great solvent, so spill it on the paint, it'll take the paint off. It will, it'll actually dissolve your paint, so people use it actually as a solvent. But the interesting thing you run into is filters, and we had a situation a couple years ago where a machine that we had developed in our department, we took it out to a cooperating farmer to test the machine on his farm. It was a multi-day test. So we took it out, we ran it the first day, it worked really great. At the end of the day, we filled up the fuel from the farmer, and the next day we worked for about an hour and the thing shut off. So the technicians ran around, tried to figure out what was going on with it, finally figured out the fuel filter was plugged up. So they took the fuel filter off, put a new fuel filter on, ran it for another hour, it shut off, looked at the fuel filter was plugged up again. Well, what had happened is petroleum diesel, over time, petroleum-based diesel has a lot of paraffins and different wax compounds in them. It'll actually build up on the inside of your fuel system, on the inside of the tank, on the inside of the lines, and all that kind of stuff. You throw biodiesel in there, it's a solvent, so it takes all that wax and stuff off and it cleans it. So what was happening is we were cleaning the fuel system on this old vehicle basically, and all that stuff was ending up in the fuel filter. And so they had to replace 3 or 4 or 5 fuel filters before they got all that stuff cleaned out of the system. Once it was all cleaned out, then it was fine. But it was that paraffin, that waxy buildup that the biodiesel took off. So those are things that you have to think about, some odd things that you'll run into. The rubber components that I mentioned. The lubricity is something else that's a big deal with fuels. So we have to have some lubricity, especially on compression ignition engines, or even on spark ignition engines that have fuel injectors. So the fuel injectors are generally a really high pressure pump that is moving fuel through them. There's moving parts and engaging that fuel. And so we'd like to have a little bit of lubricity in that fuel. It should lubricate those parts a little bit. And so that's one of the good things about fuel. If you look historically at diesel fuels had a lot of sulfur in them. The sulfur actually gave us the lubricity. It actually would lubricate the engines. And a number of years ago, for obvious environmental reasons, the fuel companies had to take that sulfur out of the fuel. So we had to go to a low sulfur diesel fuel. Well, then we lost all the lubricity. So the engines were starting to fail. So they had to find compounds that they could replace the sulfur with in the fuel to create the lubricity. Well, that's one of the things that biodiesel does. It actually provides some of that lubricity in the fuel itself. So it's not like you're adding an extra compound with potential for some emissions issues. It's actually a burning compound, a fuel compound. So lubricity is something that we always have to think about. And we always have to think about storage, how long the fuels will last. So sometimes you can keep fuels for a long time. Some fuels won't last very long. They'll go bad. They essentially oxidize, like a piece of metal will rust. They will oxidize to the point, some oxygen in the fuel was good. We talked about that with the combustion equation, but too much means it's not going to be a good fuel. It's going to be not have the power, not have the energy content, and actually may not burn very well. And so we have to watch that. And the other thing is, a lot of these fuels, biodiesel and ethanol, they love water. So they will absorb water. So if you get water around the fuel supply, they'll soak it up and pull it in. And that's bad to have water in your fuel. So that reduces your lubricity. It doesn't burn as good. There's not as much energy content. So you really have to think about how you manage your fuel supplies. And I spend a lot of time in extension. I do a lot of work out with farmers. And so these are things that I tell them on managing fuel supplies on the farm, but some things that we can all think about. And one of the tips is to fill the vehicle at the end of the day. And we don't often think about thermal effects of what's going on with a vehicle, but think about a vehicle that's been operating. Your automobile is the same way. I take a long trip. It's really, I'm out on the interstate. It's a hot summer day. The engine's hot. Everything is hot in that vehicle. And I get home at the end of the day, I park it in my driveway, and it gets really cool overnight. So think about what happens to that vehicle, that fuel that was in the tank. If I've got a lot of headspace above that fuel that's in the tank, as that air cools off, it's going to shrink. And when we have vents and stuff in the tank so that the tank doesn't collapse, and so it's actually going to pull in ambient air. What happens when it pulls in cool ambient air? When that ambient air cools off, the dew point, if the dew point temperature is relatively high, the relative humidity will be pretty high on that fuel. So we're pulling a lot of air into that tank. And so as that tank cools off, then we're going to get condensation on the inside of the tank. So all that headspace above the fuel in the tank is going to be a potential place where we can get a lot of water into our fuel supply. And so that's why we tell farmers, hey, I know it's extra effort, you're tired at the end of the day, but hey, when you come back from that trip, fill it up on the way back into town, and you're not going to get as much water in your vehicle. Okay, most of our vehicles can compensate for that pretty good, but especially on farm vehicles and stuff like that, and especially in the wintertime on cold days when you're getting lots of temperature swings, that's when we can have some trouble with water in our fuels. So keep the caps in good condition, and if you're going to store your fuel, underground's the best place because the temperature doesn't change. So if I've got a tank with headspace in it and it heats up and cools down, I got a black tank, the sun hits it in the day, the fuel expands, the air expands, it goes out of the vent, and then at night it sucks it in and sucks that moisture in. So I keep pushing out and pulling in, pushing out, pulling in. I keep pulling more and more moisture into there, and that's a bad deal. So anything I can do to stabilize the temperature of my fuel storage. So underground is best. There's a lot of environmental implications there and storage regulations, so that's usually not very practical to do, but cover them, insulate them, paint them white so that the solar radiation doesn't have much effect on them. Those are all things that can help you with your with storage and how you're going to store your fuels and so forth. Okay, so One more thing I want to look at, and I mentioned this before. Hey, yeah, we can run an engine on vegetable oil. We'll do this in lab. We'll get some vegetable oil, we'll run them through an engine and see what happens to it. Smell like French fries when it burns. So yeah, we can do that. And again, 10, 15 years ago, this was kind of a big deal. Everybody was like, oh, we're going to use all this used oil, and there were conversion kits for engines and stuff like that where you could burn this oil in your engines. So we can put a lot of stuff through, especially compression ignition engines, but we always got to be thinking about impurities and what it does to emissions and to flowability. So Crisco oil is pretty thick, and so in the wintertime it's not going to flow very good. It's going to be like a lump. So those are things we have to think about. But impurities, the fuel has to go through some standards. So anything, when you buy something that's labeled as gasoline or labeled as diesel fuel, there's a set of standards that it has to go through to be classified as that particular kind of fuel. Is the same way. So it has to follow through some classification. So those standards regulate what the cetane has to be, regulate how many impurities can be in it, what the chemical compound, the chemical makeup has to be, and so forth. And so ensuring the safety of the fuel system, that's where the standards come into play. And we're going to talk a lot more about standards throughout the semester because they're very critical to a lot of things we do, not just regulating fuels, but a lot of different things that we do in terms of design. So next thing we're going to look at, and I kind of mentioned it here, is what about this emissions? We've danced around a little bit. I want to talk about emissions on the vehicles, how we clean up, how we manage emissions, and what the regulations are for us.